Oh my goodness, you guys, you're never going to guess what happened this morning.
What happened?
So my sheepdog ran up to me and he said, so I counted the sheep this morning and there was 40. I was kind of confused and I looked at him. I'm like, Daryl, that's my sheepdog's name. I said, Daryl, we do not have 40 sheep. We only have 36. And he says, I know, but I rounded up.
Hello, everybody. You know us. You love us, hopefully, and you follow us. It's your favorite math trio, the Smarticle Particles.
Today we'll be covering reflections, rotations, symmetry, tiling, and ratios. Guiding you through this will be myself, Laura Wynn,
Cat Knight,
and me, Crystal Lambert. By the end of this lesson, you'll either have taken a really good nap or learned a lot of really cool math. Kat, can you start us off by telling us what the difference is in a reflection and a rotation?
You bet your cute little button nose I can. So here we go. So our reflection, we're going to look at this cat right here. I like to think of reflection as a song from Mulan, but it's so much more than that. Reflection is what you see when you look in a mirror. So think of like when you look in a mirror and you're wearing a shirt on and the shirt has words on it. Unless it says mom, the word is going to be backwards when you look in the mirror. So, but why you wouldn't wear a shirt with mom, you do you, that's fine. Anyway, so the definition is a transformation in which a geometric figure is reflected, blah, 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 we don't care. Let's look at pictures. So I use an arrow for the first polygon, and we're going to reflect it across this line. When we reflect it, we see that the arrow is opposite. Let's go ahead and do it again with the right triangle. We're going to reflect it across this line, and again, the triangle is opposite. So now, what is rotation? Well, our GIF kind of gives it away right here. But let's go ahead and look at it again. We're going to rotate our words. Rotation is around a fixed point. So let's rotate one more time. We're rotating that word around a fixed point in the center, which is what our definition says. So we're going to go ahead and rotate a polygon. This time not a polygon. Just kidding. A heart is not a polygon. Fun fact of the day. Let's keep going. So we're going to go ahead and rotate this heart. I did it 90 degrees. We're going to go ahead and rotate this smiley face. I did him 180, and now he's a frowny face. Anyway, so next we're going to have Laura. She's going to look at a problem that Devontae and Ephraim, I'm probably saying his name wrong, and I apologize, have done. But they've done something wrong, and she's going to point it out to us what it is that they did wrong.
All right, so Ephraim and Devontae were supposed to reflect the pattern block figure, as you can see here, but they didn't quite get it right. They needed to reflect the figure over the line of symmetry.
Hey, Laura, what is a line of symmetry?
Well, Crystal, the line of symmetry is just an imaginary line where you can fold the image in halves and the halves match exactly. In this problem, the line of symmetry is marked by the dashed orange line across the pink square. In the figure, Ephraim and Devontae they didn't reflect the figure, they just kind of rotated it 180 degrees. So Crystal, can you explain a little bit better for us what they needed to do?
Sure. So we're told that the imaginary line runs through the orange block. In this problem, we want to reflect the image, and so we know that what not to do, right? Ephraim and Devontae showed us that by rotating it, you're just kind of swiveling it around that line, and that's not what we want to do. So we're going to use this line of symmetry as a mirror. What is on top should now be on the bottom, and what is on the bottom should be on the top.
What type of symmetry is this?
This is reflective symmetry. So our imaginary line actually works as a mirror. So don't let this confuse you. Where do you see the reflection? In this case, the reflection is above and below, right? Because it's different on each side of this mirror. So when we look at it, it's a direct opposite. So our red part is directly at the top and the green triangles are at the bottom. But you notice the points in this case are pointing to the right And when we looked at Devontae and Ephraim's, in one case, because they just swiveled it around, the point went from being pointing to the right, that green tip, to pointing to the left. And that's where you see the difference in rotational and reflection in this case.
Okay, so before we can work our next problem, we need to know what reflection symmetry and rotational symmetry are.
Reflection, is that like when I look in the mirror and I look at myself?
Yes, Crystal, it's very similar to that. Reflection symmetry is where one half is the reflection of the other half. So you can fold the image in half and both halves match exactly, as you can see with this picture of the flower. That's reflection symmetry. For rotational symmetry, a shape or figure must still look the same after some rotation. As you can see with these blue stars, where the orange dot is, it's just been flipped and rotated. So it's rotational symmetry.
Okay, so now we're going to look at rotational symmetry.
How do we know if there is rotational symmetry?
So when we have rotational symmetry, we're able to take our shape or figure and turn it around whatever our pivotal point is. Mm-hmm. And when we rotate it around or turn it, it's going to end up with it's going to look exactly like the original. That's where we're going to go with that. It's going to look exactly like the original once we finish rotating it around. So our first shape, I don't know what it's called, but we're going to go with it. We spun it around, and does it look exactly the same? Does the pink version look exactly the same as the blue version? Yes. So in this case, we spun it 180 degrees and we have exactly the same look. So that is that shape has rotational symmetry. So, Kat, do you think our next shape is going to have rotational symmetry?
I do think it will.
So let's take a look at it. And our pink is going to spin in, and yes, it does match up. So therefore, we have rotational symmetry. And we're going to move on to our next shape. Now, Laura, do you think this one's going to have rotational symmetry?
I think so.
Oh, let's see. Good job, Laura. That does have rotational symmetry. Next, we're looking at our equilateral triangle. And let's see, once again, we got 3 for 3. No. Okay, so this does not have rotational symmetry because as you see, when we rotated it 180 degrees, it does not look like the original. Next, we're going to move on, and we have our semicircle, and we're going to spin that one around. It does not have rotational symmetry. And we're going to move on to our rectangle, and we spin it, and yes, we have rotational symmetry. Then we're going to go on to our isosceles triangle, and we spin that one around. It does not. So if we look at our two triangles, we can gather that triangles do not have rotational symmetry. And last but not least, we have a hexagon. And when we spin that around, what do we get? We get rotational symmetry.
Okay, so now we're going to look at reflectional symmetry. And again, reflectional symmetry has been explained as the sunflower that Laura has shown us. Think of a butterfly, and don't actually do this at home, but think of it in your head. We're going to cut this butterfly in half down the abdomen. Again, not for real. And one side of the butterfly is going to match the other side of the butterfly. Butterflies are like the perfect example of symmetry in nature. Like if there was a more perfect example, I can't think of one because butterflies, they got it. Okay. So now we're going to go ahead and move on using the same shapes that Crystal did. Do you think that this shape will have any reflectional symmetry?
No.
No, it doesn't, because this little notch is on the top right here, oops, and this little notch is in the bottom right here, and when we fold them over either hot hamburger way, this little notch is going to go on the top, it's still going to remain in the bottom. You can do it hot dog, and it's still going to be the same concept. The notches do not line up with each other. So now let's go ahead and look at our little rhombus shape. Do we think that this one's going to have any reflectional symmetry?
Yes.
We do? Well, you guys are correct. Smarticle particles, just like the name says. Now look here on this shape. Look how this shape looks the same as this. They are the same shape. We have cut the shape in half and we have gotten two isosceles triangles.
So what if we cut it in fourths? Will each of the fourths be the same too?
If it is a true line of symmetry, yes, they should all be the same. So let's go ahead and test it. Let's try to cut it in half again. And looky there. Now, instead of having two isosceles triangles, we have four right triangles that are all congruent to each other. So let's move on with our shapes. This shape is going to be the same concept as our first shape. It is not going to have any reflectional symmetry. Equilateral triangle, we're going to fold it hamburger. And we are going to have some reflectional symmetry. But if we try to fold our hot dog, the point would meet the bottom line of the shape, and that ain't reflectional symmetry. That ain't how it goes. Now we're going to go ahead and look at our, hello, there it is. We're going to look at our semicircle. Do we think that this one's going to have any reflectional symmetry? Yes, it's going to be hot dog or hamburger.
Hamburger.
It is hamburger. Woohoo! Next, we're going to look at our rectangle. We're going to go, this one has hamburger and hot dog. We can fold it both ways. Woohoo! We are grilling good tonight. Now we're going to look at our isosceles triangle. Again, this one's just got one line in it. Hot dog. And then lastly, we're going to look at our hexagon. How many lines do we think the hexagon has?
A bunch.
A bunch?
A gazillion.
A gazillion. Well, a gazillion is close. You rounded up like my sheepdog Daryl did, but this one has quite a few. So let's go ahead and knock out the hot dog hamburger. And now let's go ahead and connect our corners. But before we check, let's check and see. These are all equal shapes, right? Y'all look the same? So we know that we've got some true lines of symmetry going through there. So let's go ahead and connect our corners. Are they all the same?
No.
No, they're not, because we haven't discovered all of our lines of symmetry yet. So let's go ahead and break up these bigger triangles one more time, and let's see. Look, there we go. They're all even. We have found our 7 lines of reflectional symmetry.
Okay, so next we're going to talk about tessellations.
What is a tessellation?
So tessellations is a fancy way of saying tiling. And when we think of tiling, we commonly think of it's flat, right? So we see this around our houses, in the store, in the bathroom, in the kitchen, and this can be on the wall or the floor. So tiling is when you have flat figures and they meet together without overlapping. If they overlap, it's not a tile. It's not, it's not a tessellation. And they cannot leave a gap, so there can't be any space. So let's look here, and we have a square. And if you see, all 4 of these meet where the edges are flush, and they come to a center point. And when we look at this, that central point is called a vertex, and that's where our pattern repeats. And if we go on to the next point, we will see how this pattern will continue, and we can continue this over and over and over. And this is called a regular tessellation.
Hey, Crystal, is there anything other than a regular tessellation?
There are other types of tessellations. In this particular problem, we're also going to talk about a semi-regular tessellation, and that is when you have 2 or more polygons that can make a pattern that meets flush. Remember, side by side, we don't want it overlapping, that doesn't count. So side by side, and they have a vertex, and this pattern repeats. And they cannot have any spaces. So here you see an octagon, and we have octagon, octagon, and where that space is between the 2 octagons, you would have a square. And you can see here that this pattern repeats over and over. And as long as you have octagons and squares, you have a semi-regular tessellation or tiling.
All right, so we're going to need to figure out if this regular pentagon, hexagon, and octagon form a vertex figure.
What is a vertex figure?
Well, a vertex figure is an arrangement of non-overlapping polygonal tiles surrounding a common vertex. The interior angles that meet at a vertex must add up to 360 degrees. So in order for us to figure it out, we're going to use our interior angle formula for the pentagon. So let's bring up our pentagon. There we go. And so we're going to do 5 minus 2 times 180 over 5, which is going to give us 108 degrees. We're going to do the same thing for our hexagon. So 6 minus 2 times 180 divided by 6 is going to give us 120. And then our octagon is 8 minus 2 times 180 divided by 8. And that's going to give us 135. Now we need to add up all of those degrees. So 108, 120, and 135 is going to give us 363 degrees. So there's a slight overlapping. So these are not, so there's a slight overlapping, so they don't add up to 360. So it's not a vertex figure.
Okay, so I'm going to tell y'all one thing, and that is that I am not an interior designer, and I am not going to be an architect, but I do know math, and I do know how to mathematically apply this so that I can make my own tile figure that's going to work. But first, let's kind of look back at Myra's visually to see where she went wrong. Hey, Kat, what did Myra do wrong? Asks Laura. Good question, Laura. Thanks for asking. So let's look visually at what Myra did. We're going to go ahead. We have one pentagon is what she used. So let's kind of look at our pentagon. When we look at it, it's not very coherent. Like we see here, we've got kind of a house shape. And down here, we've got a straight line. So again, think of our hot dog fold. If we hot dog folded this, it would not have this beautiful line of symmetry. This is not a very symmetric figure. And just to prove it even further, I went ahead and flipped it, and it doesn't look the same. So these shapes, they're just not very coherent. They're not going to fit together beautifully when we put them side by side by side by side. So I chose shapes that are going to work. I chose an octagon, which, you know, think of a stop sign, stop, hammer time, all that good stuff, stop in the name of love, whatever it may be. So we're going to go ahead and use a very, very coherent shape, probably one of the most coherent shapes that we can think of. We're going to use a square. So I'm going to put a square on each one of these sides. Now, if we look, the gaps here are all equal. They all look the same, like they can fit the same shape. And that's because they can't. They're going to fit another octagon right there. And again, let's continue our shape to make sure it works. We're going to add more squares, more octagons, and this shape will continue on forever. So this is how I would tile.
All right, so for this problem, we're going to start off by drawing a line M and a point P that isn't on the line. Next, we're going to need to make an arc centered at P that intersects the line at 2 points Q and S. Then we're going to put point T not on the line M, but at the bottom, and we will make a line segment that connects P and T together, and we'll make V be the intersection of line M. So we need to make a couple sets of congruent lines.
So, Laura, what are congruent? What does congruent even mean?
So congruent means the same shape and size, but you can flip, slide, or turn it. So in this instance, the congruent means the same length. So we have two sets of congruent lines. So Q and P is congruent to S and P, and then Q and T is congruent to S and T.
Okay, thanks. Thank you, Laura. We're going to look at the triangles here now that have been created by this shape, which this shape is actually called a kite. And if you look at it, you can see why it's a kite. Unless you didn't have a childhood, then you don't know it's a kite. And I'm so sorry. But we're going to call this a kite. And the kite has one line of reflectional symmetry. So, and that would be hamburger. And the line is drawn already for us. Reflectional symmetry, P to T, is going to be our line of reflectional symmetry. So now we're going to look at our triangles. So let's look at QPT and SPT. And like I have explained before, that when we cut a line in half with a true line of reflectional symmetry, each side is going to be the same. So we can tell that that's going to be the same here. But if you're in doubt, let's go ahead and look at these congruent lines. So this line.
What are those little lines on the bigger line? What do those mean?
I'm going to go ahead and call them little tick marks. But this little tick mark and this little tick mark means that these lines are congruent. They're the same. So we know that they're the same length. That line is letting us know. So if maybe there's a little doubt in your head, you couldn't quite tell that they looked the same because of optical illusions or your eyes playing tricks on you, whatever the case, we know without a doubt that these are congruent lines. Same down here. So these two are congruent to each other, and these two are congruent to each other. So we know for a fact that those two lines are the opposite but congruent to each other. And then the triangles share a base. So they have to be, so that has to be equal. So that's how we know that these triangles are going to be equal to each other.
So we're told that angle QVP is a right angle.
What is a right angle?
So a right angle is 90 degrees. It's equal to 90 degrees. And that's often when you see that little cute little square that comes in. But this looks like 90 degrees to us, right? We look at it and visually you're like, oh yeah, that's 90 degrees. We know it. And yeah, but that's not always true. Sometimes it can be off a little bit. So when we notice that the angles of, the first thing we notice is that the angle of QVP and the angle SVP are adjacent and supplementary.
What does it mean that the angles are adjacent and supplementary?
So angles are supplementary when there is a sum of 180 degrees and they are on the same side of the line. So we look at this line M and angle QVP, angle SVP, they both come up, right? And they have that. In this case, we also share, well, we're going to talk about adjacent. So angles are adjacent when they have a common vertex, and that's that V, and they have a common side, and they share the line segment of PV. So in this case, we know that angle QVP is, in fact, 90 degrees.
Okay, thank you, Crystal. For our next problem, we're going to inscribe a triangle and a pentagram within a circle.
Hey, Kat, can you explain what inscribe means?
You bet I can. So we're going to go ahead and start out with our triangle. To inscribe this within a circle, we're going to put a circle around our triangle, but all corners of the triangle have to touch the circle. So we're going to go ahead and do that again with the pentagon. Just kidding, it's a pentagon, not a pentagram. We're going to go ahead and inscribe that within the same circle. And again, all the points are touching, so we know that we have successfully inscribed it within the circle.
All right, so now we must find the measurement of angle NOQ. To do that, we're going to use angle bisectors.
What are angle bisectors?
It's a good question. An angle bisector is a ray that starts at the vertex of an angle and splits the angle into two congruent parts. So inside our circle, we have a pentagon, which has 5 sides, but when you use the angle bisectors, it produces an inscribed regular decagon, which means 10 sides. The equilateral triangle has 3 sides, which produces an inscribed hexagon. Now with all the angled bisectors, we have 15, since the two shapes share a point at P. So a circle is equal to 360 degrees. We divide it by 15, and that gives us 24 degrees. So angle NOQ is 24 degrees.
Okay, in our next problem, we have Jenny, and little Jenny is gone, and she's looking at this cliff, and she needs to determine the height of the face of the cliff. So the first thing we're going to do is look at, what do we know? So this is what we know. We look at our word problem, right? And we take out some nifty little facts. First, we know that Jenny, from her eyes to her ruler, because she's standing out there and she has her nifty little ruler out in front of her and she's looking, and her ruler is 2 feet in front of her eyes. Then our next fact that we get from our problem is that when she's looking at the face of this cliff, the difference between the where she can see the top of the cliff and the bottom of the cliff is a difference of 1.5 inches. Then we also know how far away Jenny is from the actual cliff. She is 1/4 mile away from this cliff. Well, the problem also lets us know that 1 mile is equal to 5,280 feet. And from there, we're looking at our triangles, or we know that our triangles are similar.
Well, how do we exactly know our triangles are similar?
Well, as we look at this, we know we have two isosceles triangles. We're given the bigger triangle from her eyes to the top and the bottom of the cliff. Then the smaller triangle that we see here is from her eyes to the ruler. And you can see that angle is the same. It starts the same from her eyes going out. It just goes at a gradual increase.
All right, to get started on the next step of the problem, we're going to need to convert everything to the same measurement. So we're going to convert everything to feet.
Why feet?
That's a good question, Kat. We convert to feet because everything needs to be the same unit of measurement in order to solve the problem. The measurements given to us were miles, feet, and inches, and the only measurement that gives us an easy numbers to work with would be feet. So now, Kat, after we do our conversions, there we go. 1/4 mile is 1,320 feet, and 1.5 inches is 0.125 feet. Now, Kat's going to finish solving the problem for us.
Okay, so I have to picture back again just so we can see Guinea, Ginny, whatever. And to solve this problem, we are going to do cross multiplication.
What is cross multiplication?
Laura, did you hear her? She said what's cross multiplication? She don't know what cross multiplication is. Girl, I hope you're ready to learn what cross multiplication is. Cross multiplication is the best thing to ever happen to math. It's my favorite thing to do in math. And we're going to use it to solve this ratio. Okay? So we're going to set up a ratio. We're going to put distance between ruler markings on top, which we know is the 1.5 inches, and distance between Guinea's eyes and the ruler, which is 2 feet. We're going to put that with height of the cliff, which is what she's looking for. That's the congruent part of the ratio over the 1/4 mile. So now let's plug in our numbers. Got 1.5 inches over 2 feet equals x over 5,280 divided by 4. The divided by 4 is because it's a 1/4 mile, and there's 4 and 1/4. And the x is what we're looking for. So now let's go ahead and, Laura converted it for us. So we're going to put in our conversion numbers. And now here's where the cross multiplication comes in. We're going to multiply the two numbers where we're actually given two numbers. So we're going to multiply 1,320 by 0.125 feet. And then this number is all by its lonesome, so that's how we know that that's the number we're going to divide by. And when we do that, we're going to get 82.5 feet.
Wow. Thank you, Kat. So that's all we've got for you today. And thank you for staying tuned and joining the Smarticle Particles on our math journey.
Thanks for joining us. We hope to see you again soon, although we probably won't. It's the end of the semester.
And as always, stay smart, stay sharp, and stay a rock star.
Bye.
Bye.
End it anytime now.
I think I'm having hot flashes.
I know I haven't ended it yet.